ready, sir? This is your first one.
Hello, welcome everyone for this live session on micro and nano fabrication course. Looking forward to answering your queries on the course. We already have a few questions. So the first question is about the deposition of graphene on a substrate. Is it possible to do it? The answer to that is yes, one can deposit graphene, but then there are different ways to do that. Graphene as a 2D material cannot be grown just on the substrate yet, because it needs a lattice matched substrate in order to grow a monolayer of graphene. So normally graphene is grown on copper. So then the grown layer is transferred onto the substrate. So there is a transfer technique that people use in order to transport graphene from a copper substrate onto a silicon substrate, right, if you want. But then if you want to grow it on copper, then you can do it. But then you can also grow graphene on other phase match substrates as well. So it depends on what kind of substrate you want. If your substrate of interest is silicon or silicon dioxide or nitride, silicon nitride, then you have to do this transfer. So either you can grow graphene on copper substrate and then transfer it, or you can do exfoliation. So you have a thick graphite and then you can exfoliate layer by layer. Right? It's called the Scotch tape technique. By using that, you can remove a monolayer of graphene, and then you can transfer it onto desired substrate. And you can also do stamping process. Right? This is all done using a physical method or mechanical method of transferring. So a simple answer to that question is yes, but there are many options, right? Based on what substrate and how large you want to do and so on. And next question is more administrative. The question is about what will be the model of question in the final exam. Right? So the question, the nature of the question, and also the complexity will be similar to what you have seen in the assignments. Right? We have different sections. Right? So we have the recall section that when you go through the lecture, there are questions that will ask you to recall some of the concepts that you studied, formulas that you might have seen. That is the recall section. And then you have application section where the concepts are applied. Right? So it's similar to assignment, but it's not exactly the same questions. It will be of similar nature. Yeah, you can expect a large portion similar to your assignment, but then you will also have portions that are slightly different, where you have to apply your understanding to solve some of this problem or some of this question. Okay, so that is the second one. So hello Pranav, good to meet you here. So if there are any questions, queries, you can always post. Looking forward. Hello, Manjeet. Welcome. Yes, Manjeet. The question is about reference book for lithography study. Right? Um, so as you might have seen going through the course, um, a lot of these things are not covered in any conventional fabrication textbooks, and it is hard to find these basics elsewhere. It's good that we would like to study more on this lithography. Um, the reference book that you can use if you really want to dive deep into lithography is Lithography by Chris Mack. Okay? So Chris Mack book is a very good uh, reference for optical lithography. Uh, so not all the lithography put together. Optical lithography by Chris Mack is a very good reference. But you can get lost in that book because it goes deep into each and every process, as we have done in the course, right? So we have understood the importance of spin coating, importance of photoresist process, um, and then imaging process. So we have dived deep into it, um, but this book is even deeper. So if you are really excited about lithography, this is a very nice book. Okay, Optical Litho by Chris Mann. And some of the optics you may not be imaging optics, you may not be able to find it in this reference, um, because that is all coming from my own experience in using this complex optical lithography tools. Okay, so perhaps I should start writing a book on this, where to complement whatever we have. But that imaging part, perhaps you won't find it in Christmas. But then, all the individual processing that we went through, optic resist processing, development, post-exposure bake, all those things you should be able to find it with very detailed explanation. Thanks for that question, Manjeet. Okay, so we have an interesting question from Pranav. Uh, Pranav Pradeep. Is it possible for deposition systems of a single crystalline material to show good growth from deposition point of view, but still show inferior property when compared to bulk? Very, very interesting question. Um, so when you take a single crystalline material, most of these properties that you study in literature, right, as a material scientist, it's mostly on bulk uh, material. So the bulk material properties could be very different from a thin film material. A good example is ferroelectric materials, for example. Right? So ferroelectric materials are a good class of material, right? So where um, the aspect ratio is very important because it's an anisotropic material. Right? So when you make a very thin film of this material, there are stresses involved. and the stress could actually modify the polarization in this material. So when you grow a bulk material, then they relax and there is no stress involved. But when you start growing a very thin film of this crystalline material, right, it's a very good deposition process that you have without defects and everything. But then you are growing it on some other substrate. Right? In a bulk material, there is no interface. So when you are doing a thin film growth, you will have interface. So these interface will create stress between this, and this stress will cause um, polarization effects in the thin film that you are interested in. And sometimes it works for your advantage. Sometimes it is it might be detrimental to the properties that you are trying to exploit, right? So there you have it. I think it is very true that thin film properties can be different, or the magnitude of the property could be weak when you take a thin film compared to a bulk. But you have a lot of other interesting things come in when you have stress. So you can also play with stress and improve these bulk properties when it is thin. Okay, so one of the important thing is associated stress. Okay, and the relaxation of the material and so on. This is primarily for anisotropic materials, and if you take amorphous material, you don't see any effect from bulk to a thin film. Okay. Um, so Ria Goyal has asked a question on or guide on interface neurons with biomems. Um, I'm not sure what Ria is trying to ask here. Probably how do you interface neurons with biomems? Right. So MEMS is a uses heavily the micro and nano fabrication process where we can make mechanical structures, and you can use those structures for multiple purposes, primarily used in sensors, right? Gyroscopes, accelerators, and so on. And recently, people have started exploiting MEMS for bio applications as well, where you can look at mechanical properties of, for example, cells. Right? So you can take a cell and then probe the mechanical property using this mechanical structure, and probe the nature of this cells, right? Whether it is an infected cell or whether it's a healthy cell. When it comes to neurons and neuron interfaces, it's slightly tricky with MEMS. So MEMS can be used, or patterning or large scale patterning could help to grow and cultivate neurons, right, in a systematic way. So you can make a pattern and then restrict the growth in a certain way. Right? That will help you to control the pattern of neuron growth. But then if you want to interface neurons with mechanical structure, it's because they're fundamentally different. Mechanical stimulus were primarily of electric field induced and mechanical force induced. Right? But then neurons, they also give out electrical signals, but these signals are rather weak to activate any mechanical structure. If we can think about NEMS, right? So we can really reduce the structure size, and you can reduce the spring constant and everything, so that you need very small amount of voltage in order to activate, or in order to link between these neurons and MEMS structure. So those could be of interest. Right? That is really pushing the technology, where you are using um, spiking neurons, and those neural signals can be used to trigger a mechanical structure. When I say mechanical structure, it could be a very thin 2D material, for example, right? Or a very thin membrane that you can do it. So you have to scale down your force requirement in order to make these interactions happen. It is doable, and it is extreme engineering. Thank you, Ria, for that question.
Um,
Right. Thanks for this question, Manjit, about materials, right? So the question is, when we say crystal plane, silicon 100, how this is different with respect to 010, 001, and other planes, so 111, for example. The question here, it seems like we are just changing direction, but the rest of the things are remaining same. Right? It might look like everything is same, but it is not. Okay? So the reason for that is silicon is a a centrosymmetric crystal, right? So these different crystal planes, I mean, though the atomic arrangements are they are not same actually. When you are rotating it at about so all these crystal planes, they got their own surface energy. Okay, so the energies are different. Okay, and this is one of the reason why in your wet edge directional wet edge discussion, you would have seen that you don't need to pattern it when you do an anisotropic edge like KOH, potassium hydroxide. When you use it on silicon, it etches under a certain plane. The reason for that is the available energies, right? So the surface energy is so low that it can etch faster compared to another plane. So the atomic arrangement, the lattice would look the same, but it is not in terms of energy, right? And this lattices are also different. Okay, so the lattice constants when you move from one direction to the other direction, it is also different. Because of that, one silicon is very different from 100 silicon because of the atomic arrangements that you have, right? Or the lattice constant that you have on the surface are going to be different. Okay, so you cannot plainly say that it is all same, right? It is not, because there is a lattice constant difference that you see. Right? All right. So we have few interesting questions. So we are waiting here for a few more questions, right? So if we don't see any questions, then we 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 actually close this session. But I see few are already there, but yet to ask some questions. So I encourage you guys to ask whatever doubts you may have, so that you can clarify. Okay. Um, Manjeet, the question is prerequisite for photonic integrated circuit course. Uh, so, since photonic integrated circuit course more or less falls under the category of elective courses. It's not a basic course. It's an elective specialized course and looking at next generation technology and so on. Um, so if you have a background in photonics in general, so there is a course on introduction to photonics uh, in NPTEL done by Professor Balaji Srinivasan from IIT Madras. So that's a very comprehensive course on photonics that covers all the basics. Um, but nonetheless, if you have a background in electromagnetics, right, and if you have interest in electromagnetics, then I think photonic integrated circuit course you can still take it. Right? A basic understanding of waves and electromagnetic waves and um, understanding light, right, interaction of light, um, is good enough to take that course. But I strongly encourage you to just have a look at some introductory photonic material so that it will be not too intimidating to look at photonic integrated circuit course. Right. Um, that's an interesting question, Manjeet. So when we say 2D material, it means only one layer of material or more than one layer. Um, but electrons are not allowed to move in Z direction. So when we say 2D material, what we mean by 2D material is a single monolayer or few layers. So we call that as 2D. Um, we call that 2D from the functional perspective when the property of this uh, material, the thin material, right, um, is very different from the bulk, right? Let's say. So then you characterize that as a 2D material. So when you keep on stacking it, then you go into the bulk behavior of that material. A good example is molybdenum disulfide. So MOS2. So MOS2 is a direct bandgap material when it is a monolayer, right? I think it's 3 layers or something, where it's still direct bandgap. But then when you increase the layer thickness or number of layers, it becomes indirect bandgap. So it starts to show bulk property. So the thickness below which you clearly see a transition, right, in properties, we can call that as 2D material system. This may be just a single monolayer or few layers. You're still okay. We are not putting a constraint on you only call it as 2D if it is less than 3 monolayers or 4 monolayers. We are not doing that. It's from the functional perspective and property as well. And the other thing is about your electron transport assumption. It is not true that the vertical transport is not allowed. The lateral transport is much better because there is no availability of states to go higher. So your transport happens along the plane, but it is not true that they are not allowed to move. Right? You can confine them. Right? But when given an opportunity, when you have layers, right, for charge transport, you electrons does this vertical transition as well. So they do move in the Z direction. This is heavily exploited when in some of the optical and also um, optoelectronic devices, right? So where you generate the charges, and in order to collect the charges, right? When you start to move along the plane, because of the defects, you might, fall into a trap, or you can anneal the charge there. So you might lose the charge. So in order to avoid that, the best way is to, once the charge is generated, you just pick it up from a layer on top, what you call the charge collection layer. That is perhaps another 2D material layer, right? And then you can take your charges out. So vertical transport is allowed, right? You can actually make it not, confine it, and not allow move in Z. But then, it's up to us to engineer the energy, right? To allow or not allow the propagation in vertical. It's an interesting question. Thanks. Okay, I don't see any questions so far. There is another question from Mandeep. Which PhD is better? One which solves small problems of society by using technology, or big things which is restricted in papers? So that's an interesting question. So when you're doing a PhD, you have two routes that one can take, but both results in impact. Okay. So whatever you do, you try to do to create impact. Right? So the impact could be to a wider scientific community or social impact. So whatever impact that you create in a wider scientific community, it's delayed impact to the society. That's how we see it. So today's papers are tomorrow's technology. So even we have, PhD in technology, at least in my group and also in our department and a lot of departments here at IISc, there is a clear focus in developing technology that has a direct societal impact. So PhDs are not just to create papers. Right? So you do create technology, but you can also publish papers when you create technology. So one need not differentiate that if you do things that are of importance to society, you won't be able to publish. Right? It's all about your perception. So right now there are um, projects that are run by PhD students where they are looking at problems related to agriculture, where we are developing sensors that will have direct impact to farmers. How do you do precision farming? So if your question is this a topic for PhD? Definitely. So we are developing technology that will have a direct impact to our society. At the same time, we are developing very interesting understanding of, uh, in some of these cases, mechanical and chemical. So this is done in one of the mechanical engineering departments where people are looking at how heat waves propagate through a medium, right? And using that technique, you can understand the soil, nature of soil. And in another department, we look at shock waves going through medium in order to understand the earth composition, right, the density. So these are all very fundamental questions to ask, but at the same time, it has real impact on the society. So we develop in our group, communication and also sensing related activity by using light. It might look very advanced technology using light to do, particularly on a chip, to do these kinds of sensing activity. But then what are we sensing for? So we are sensing chemicals here. We are sensing, bio analytes that has direct implication on diagnostics and health monitoring, right? Which translates to societal impact. So this is not done, as a separate work. This is all done by PhD researchers. So you did not, differentiate PhD from, one that has only paper component and one that has technology. So it's up to somebody's interest. For example, we still have very difficult problems to solve in quantum mechanics. Right? How do you understand things at quantum scale? Um, you may wonder that whether this will have a societal impact. It will down the road. If we don't invest and put our brains together today, tomorrow we will not have that impact on the society. So it's all about your perspective on this technology and science and paper and so on. Thank you for that question. Are there any other questions from the participants here? And if there are no questions, then I request you all over there to put your questions in the forum, right? I'll be more than happy to answer those, right? And we should be able to do that. I see one more question from Manjeet. Can we make mask not in chrome glass but using transparent material like plastic by printing with maximum resolution? Absolutely, absolutely. Uh, Very interesting question. Just to give you an example, you can take a OHP sheet, right? Transparent OHP sheet, right? And then print things on this OHP sheet. You can print out a millimeter size or even micrometer size printing, right? Which is possible now, because these days the printers got very high resolution, and micro printers are also available. And if you can print those structures on this transparent sheet, why not? We can use it, and we use it in my lab actually. So we take a simple OHP sheet. These structures are pretty large. This is used for sensing application where we use to create fluidic channels. So there the structures are very large. Right? So you're talking about a millimeter in width and probably centimeter in length. You don't need expensive mask and to be fabricated for this. So we simply use OHP sheets, and then we print dark ink on top of this, and then use that sheet for lithography. We do that, and one can do that. It's relatively easy to do and very cheap as well. But the only constraint there is the resolution. Right? You cannot make nanometer scale features. Right? It's going to be slightly broader, larger, uh, right? But then, if you are happy with the larger features, low cost, why not? We can certainly do it. You just need a transparent sheet and then an opaque structure. You can do that. That's an interesting question. Thank you. Is there any other questions? All right. There are no more questions. Thank you everyone for joining this online session. I appreciate all the questions. Some of them are very interesting, and some of you may have more questions. So I request you all to post the question in the forum, right? So that we can get back to you with clarification. Thank you very much for joining.